don't know. I'll talk to you about it later. It's just weird. There's several people in this school who come up to me and, well, not unlike twice, though, but adults, and they'll talk to me about things and rant, kind of like, and I'm like, okay, I guess I missed that. So it was weird. I was like, oh. Anyway, whatever. So today we're going to be talking about Newton's method. / linear approximation. Now, if you didn't write those down in order already, maybe you want to flip-flop them around. Okay, I'm probably going to start with linear approximations first. You're like, well, Mr. Groom, didn't we already do tangent lines? We did. So is it going to be a lot different than that? No, but we're going to do something different with it. Okay? So it's not hard, it's not really different than that, but we're going to do something different with it. And then, here's the kicker. Once you got it set up, you can do other cool things with it, one of which is what we call Newton's method. Okay? So, here we go. So, without further ado, let's have a function. I don't know, 3x cubed plus 4x plus 1. Hallie says, let's do it at x equals 1, Mr. Groom. Okay, cool, whatever. Now, here's the dealio. Near any point, I can make any function look straight. Is that true? If I zoom in tight enough, is that true? If you zoom in tight enough, you're like, this is curvy. No, it's not, it's straight. Over a very short interval, perhaps, yes? Now, we know that we could write an equation that looks like this, y equals mx plus b. We know we could, and we're going to, sort of, in a moment. But allow me to refresh your memories for a moment. Do you remember this equation? And of course, the right answer is, of course we do, Mr. Groom. Well, it's just the slope formula is all right. Brooke, this is exciting. No, you don't even know. This is totes exciting. Okay. See, I'm going to give you an x, let's just say an x1. You with me? Well, if I give you an x1, then you totes know this fella, don't you? F of x1. I mean, you can totally find it, right? I feel like you could, right? And then I feel like you could find this guy at that value, couldn't you? Does that make sense? You found the derivative at that value, right? In this case, 1, the case we're doing right now currently, yes? Now, allow Mr. Groom to do some substitutions. And I'm going to lose the y2's for just a moment, so I'm just going to go f y minus like that. Is that okay for everyone? And I'm going to make, after you get that written down, I'm going to make one little slight modification to that. Right, this is just some f of x instead of y. That's all. Okay. Now let's do a little algebra, shall we? Right? All I do is cross multiply. And then watch this last one. So I'm going to say f of x. I'm going to leave it equals for right now. It's not going to be truly equals, but I'm going to leave it equals for this second. It's going to be this guy here. Okay. And in reality, Jacob, what's going to be, it's all of you, all of the Jacobs. It's going to be that. It's approximately that. There's like 27 of them in here, apparently. We missing one? Whatever. All right, so here's the deal. Here's my function doing whatever it's doing, right? Here is, like, say, x1 right here. So let's just say this is x1. That's where it's at, whatever, right? I could write an equation for this line, yes? Right? And near this value, what's happening on this equation here and what's happening on this line are the same, yes? Now this, when I did it here, they happen to be pretty curvy, so I can't go out very far, yes? However, if a person asked you through this region here, that's really linear right there, isn't it, right? Or if my equation was along in here somewhere, well, you could go out quite a bit further. But here it's pretty darn curvy-worvy right there, so obviously you couldn't go out too far. Now, let's zoom in, shall we? Ooh. Hey, look at this right here. Check it out. This is our x in question. Maybe? Notice what it is. It's something like x1 plus a skosh. Are you with me on this? Right? It's just a little bit more. Does that make sense? 0.1 maybe. I don't know. I just work here. Don't get mad. Now look, right here. Check it out. Right there. This right here is an approximate value. Yes? This is the actual value. Yes? Are they pretty close? Ish. Ish. Now Lily says, Mr. Groom, couldn't we do like a quadratic fit or a cubic fit? Yes. And we will start sometime next chapter, sometime next semester, we will do what are called Taylor polynomials. In fact, if you were trying to hide, like if you were identical twins, would it be hard to fool a substitute teacher who's never seen you before? No. Because you look the same, whatever. Would it be hard to fool your friends maybe that don't, your acquaintances? Maybe a little trickier maybe. Be hard to fool your mom? Wow, it would be hard to fool your mom. Okay? You'd have to be a lot more. You'd have to have a lot more in common, right? Other than just the face looking the same, yes? And so later on we'll do that. But for today, look at this. They have the same value in question here, right? And they have the same slope right here, right? So it's pretty close. So these two values will be ish close for today. So what is called linear approximation. And down here is the formula right here that you need to see. There it is, dog. Boom. That's it. We will use this formula again and again and again and again and again and again. We should find out today what happens when you plug 1 into this formula. Check it, but I think you get 8, right? So, 8. That was easy. Check it out, dog. What? Hey, what's the slope at 1? I don't know. I better find a slope. 9x squared plus 4. All right? Plug a 1 there. What do you get? 13? 13? What did I say? Let's see. Hey, there it is. Ta-da! Mr. Groom, should I distribute that? You know, I wouldn't. And here's why. Today, you're going to be asked the following. Lily, can you tell me approximately what is f of 1.1? Yes, you can. So Lily's going to do this. Check it out. 1.1 minus 1. Right? Plus 0.8, or plus 8. So this is 0.1 times 13 is 1.3 plus 8. So it's approximately equal to 9.8. That's it, right? What? 3. Whatever. You know what I mean. Good for me. Okay. Now, there is a method to our madness. Again, this is a first step in a long process called Taylor polynomials, which we're going to get into a little bit next semester, okay? But it's the first step, okay? Now, we all have freaking calculators, so we can all just freaking graph it and type in 1.1 and blah, there's our answer. That is not the point. You understand that? This is a first day of a long setup of what we're going to deal with, okay? So don't get all, why am I doing this? This is stupid crap. I don't want to hear about it. Okay. Now, take your calculator if you would, or some Droid mobile device or what have you. Go back to the original equation. Plug in 1.1 just for fun. I'd like to know how far off I really am. That's what I'd like to know. Seriously, what's the matter? Okay, you look mad at me.
Don't believe that answer. That's not a real answer.
Well, I've been around long enough to know that's part of an answer. I'm not going to push it, whatever. But if there's anything I can do, you just go ahead. Shut up! It's what?
9.393.
9.39. Oh my gosh! Hey, that's a pretty good approximation, dog. Nice. Is that good for you, Lace? It's not bad, huh? All right, let's try another one, shall we? We need a function. Somebody give me a function. F of x equal to? Thank you. Square root of 5x. Love it. Plus e to the 2x. Totes love it. Plus 5 minus 3 over x. Because why not? Hey, where do you want to evaluate this at, Hannah Morris? X equals... Okay. Look, I'm okay with that. You can't scare me. I'm okay with that. Now, let me just ask you this question. Before I say where do you want to evaluate at, maybe I ask the question this way. Can you tell me approximately what f of 6.7 is? Well, what's a value that's awfully close to 6.7? Hannah? 7, I know. You get it? So I'm going to use 7 because it's awfully close to our value in question, yes? Nice. So what do I need? Well, I know this to be true. I need this f of x is approximately equal to f prime of x, whatevs, times x minus x1, this is x1, plus f of x1, right? Something along those lines? So let's do it one piece at a time, just like Johnny Cash. Let's plug 7 into this mess, see what you get. I got it one piece at a time, and it didn't cost me a dime. If you've never heard that song, A, I'm sad for you. B, you should go watch it. It's a great song on the YouTubes. What do we get? We're plugging in 7. What do we get? What do we get? I like it when we hook up the wire. There's 2 headlights on the right and one on the left. When we pulled the switch, all 3 of them come on. That's my favorite part of the song. We'll have to play it later. It's exciting. Because he stole the car from GM as a Cadillac. He stole it like over 20 years, so none of the pieces and parts match. He snuck out in his mobile home and his lunchbox and whatnot. He put it all together in his garage. And yeah, he had a fin on one side, not the other side. And it was pretty hot. Yeah, it's a good song. Classic. Wait, what'd you get? What happens when you put 7 in? I want to know. Do I have to do it myself? Oh, golly, I have to do it myself. 1.2.
10 to the 6.
Holy buckets. Do you mind if I make this 1.7 instead? Is that okay with everyone? Then this would be 2. Then my number wouldn't be so god-awful ridiculous. Is that okay if we do that? Because I feel like e to the 14th is a little ridiculous. Yeah. It's just a little ridiculous. If I hadn't gone with e to the 2t, we'd been aight. But what do you get?
62.26.
Oh, hey, I buy that for a nickel. So 62, that's for this guy right here, right? That's important. That's f of 2, right? Is 62 point, what'd you say? 0.26. Beautiful. Nice. We need a derivative. Let's make it happen. What is the derivative of the square root of 5x? I don't know either, so I write it like this. So it's 1/2. Do it piece at a time, right? So 1/2, 5x to the minus 1/2 times 5, right? So it's 2.5, right? Over square root of x. So I'm going to write that somewhere. 2.5 over the square root of x. A variety of ways square root of 5x rather. The variety of ways a fella could write that, whatever makes you happiest. What's the derivative of e to the 2x? 2e to the 2x. What's the derivative of 5? Nada. And what's the derivative of negative 3 over x? Well, remember, that's 3x to the minus 1, so... Oops. What's the derivative of that? 3 over x squared, right? 3 over x squared. That's right. Nice job. Nicely done. Now, this is our derivative. Hot dang. Let's throw, what are we throwing in there? Let's throw 2 into this dog, shall we? You get it? What did you get?
110.
Exactly?
110.237.
110.23. But that's a pretty steep slope, by the way. Am I right? Yeah? It's pretty nuts. X minus what? Minus 2. So as long as you were in the ballpark, you see, of 2, this should ought to work, yes? So what happens when I plug 1.7 into here? 1.7 minus 2 is negative 0.3, right? Right? Well, what do you get when you do that? So this 110.23 times negative 0.3, what do you get? It's a negative value, by the way. I'm shocked. So negative, this is negative 0.3 right here, times that. So negative 32? Negative 33.2. Is that what I got? I don't, I'm just asking. I feel like my hearing aid turned off or something. I don't know. Okay, and then when you plus that together, what do you get? I don't know. I don't know. 29.19. Or thereabouts. Okay? Or thereabouts. Okay? Now, a fella could, if a fella wanted to, or a lady, whatever. Not judging, just saying. Here we do this. Yeah, read me the original function there. It's square root.
Square root of 5x.
No, that's 4x, dummy. Try 5. There you go. Go ahead.
Plus e to the 2x. Plus 5.
You're too fast, bro. You're killing me, Smalls. All right. And then what?
Plus 5.
Mm-hmm.
Minus 3 over x.
What? All right, cool. And then let's give it one of these and some of that and one of those. And then was 110, is that right? 0.23. X minus 2, right? Plus 62.26. Ooh, interesting. Now up here at 2, what should happen? At 2, they really ought to, what? They really ought to match is where they hit. Why is it not exactly at 2? Because we rounded off. Okay. Notice how the blue and the red are nearly indistinguishable at this point, yes? They're nearly indistinguishable. Yeah? Now, I'm interested here at 1.7. So if a fella were to trace this out a ways back, we're still above 2. I don't care. I could figure it out a different way, but I don't care. I'm going down here. My gosh, I still feel like they're right on top of each other. You see this? I feel like they're right there. Ooh. See how they're starting to separate? What? I can't read it though. 1.7 is right there. And they're like literally on top of each other, aren't they? I'm on the red one. That's the exact value. 36, right? What was the blue one? What did you say the blue one was a minute ago? We just said it. You told me a minute. What was it? What was the blue one? What did you say the blue one was? Somebody mucked it up, didn't you? You're telling me you mucked it up. You said it was 29.
Yeah, I said it was.
For God's sakes. What is it really? Is it not really that? I don't know. Whatever. So the point is we're pretty close in the ballpark there. Okay? Yeah. I feel like somebody messed this up. I feel like something in here is a little goofy. All right? But I'm not going to cry about it right now. I'm okay with it. Okay? I'm okay with it right now. Now, that is linear approximations. Okay? Which we've done some of, sort of, but not exactly, but whatever. Now, the second part of our lesson today is we're going to do the same exact thing, except with one changeo. We're going to talk about what is called Newton's method. And Newton's method is just a way of finding roots, or if you prefer, zeros, yes? But in reality, Brooke, it's just taking what we just talked about today and turning it on its ear just ever so slightly, yes? Here's why. Here's my function. Wah! 1, 2, 3, 4. Somewhere between 3 and 4, what do we have? A 0. Yes? Everyone see that? Allow Mr. Groom to just allow me, if you don't mind. What if Mr. Groom chose x equals 4 for his initial value? Okay. Hypothetical. Yeah, by the way, could I have chosen 12? Yes. Is it going to work as nicely? No. You should always go as close as you can. Initially, it's going to take less farting around to do that. Allow me to come up here and make this point right here, yes? And allow me then to construct a tangent line. You mean basically like we just did 2 minutes ago? Yes! Now look down here. This is the important thing, folks. I want to know, Lacey, I want to know the x-coordinate of this point right here. Do you see this? Ooh, but I feel like this x-coordinate is pretty close. You with me on this? It's not quite there, is it? So, Lacey, what we're going to do is we're going to take a new value. And we're going to say, Mr. Groom, let's let this be our x2. And then let's fit an equation so that it's parallel, oh my gosh, right there. Wait a minute. Now, where this red line crosses the x-axis and this fella here crosses the x-axis, they are what? Pretty close to the same. Could I get closer if I did it again, and I did it again, and I did it again, and again? And we call that an iterative process. It is the idea that you get out an answer and you run it back through to refine it. Go ahead, good job. Now try again. Good job, good job. Not unlike in practice when you hit the ball. Well, good try. Now hit it again. Oh, you're getting better. Try again. Okay? Now, the algebra of this is, oh my gosh, so easy. It's disturbing. It really is. So follow with me if you would. We know this. What? We know that this is, basically the same exact deal we did a second ago. I'm going to write exactly the same way I had it a second ago. Okay, I'm going to start from there. Everyone go with this? I'm going to change it up just ever so slightly. This is the important part. It's not always going to be the first. It's going to be the nth place. So this is going to be f of xn plus 1 minus fx sub n. Oops, this should be n plus 1. Sorry, my bad. My bad. My bad. Okay, this is where it gets really cool. Are you ready for this? Let me draw the picture again. So, random spot over here. Wah! Here is xn, if you will, yes? This point up here is xn, f of xn, whatever. Right? Down here, it's going to come down here. It's going to cross and hit like this. Which, of course, this point is xn plus 1, f of x n plus 1, right? Well, technically, yes. But what is this fella going to be every single stinking time? Right here. 0. Are you with me? That is key. Do you see it? You mean this number on top is just going to be 0 right here every time? Literally, this is true. That makes sense? No? What do you mean no? So I found this point right here, right? So I gave you an xn. You find a y to go with, yes? You find an equation of a tangent line, yes? It crosses this point down here, yes? At some new value, n plus 1, right? And some new y value, yes? But because it's on the x-axis, it will always have a y of what? 0. That's it. That's all I'm saying. Okay? It's very good that way. Now, so again, it's the exact same basic formula. It's tweaked a little bit. Makes it look a little different. Now, allow me to cross multiply, yes? And so if I do this, I will end up with this fella on one side. Now look at it before you say, how did you do that? Just look at it for a minute. It's very easy. Do you see how I did it? How did this get down here? How did this fella end up down here? I divided, yes? And how did this crap get off the bottom? Times it. We're good to hear, yes? Now, what do I want to solve for? I want to solve for xn plus 1. So it's negative f of xn ta-da! I give you Newton's method. Now, if you have your TI calculator or your Desmos.com device or something, get it out, because we're going to do one. This is the deal. This is what you must have. Now, you're like, wait a minute, Desmos, is that really what you want, Mr. Grimm? Actually, I don't want Desmos. If I have my TI calculator, that'd be great. But wait, don't put your phone away. If you have your phone out, go to Google Sheets. Because what's even better than a graph for this, because we're not going to use the graph if we have our 89s, we're going to use a table. What's even better for this is using a spreadsheet. It's a beautiful thing. So, let's make it happen. So, we need a new function. So, do we have a function here? Let's do x cubed minus 7, shall we? And I want to know, where does this guy cross the x-axis? I don't know, Hallie, but I do know that 2 cubed is 8. Are you with me? So, and I know that 1 cubed is 1. So, somewhere between 1 and 2, I'm going to have a 0 for this thing. Are you right? That make sense? Right? Because if it was 8 minus 7, it'd be 1. And 1 minus 7 would be negative 6, right? So somewhere between 1 and 2, I've got a 0. Is that clear? Now, my initial value this time, my starting value, you could call it x naught or x1. I don't really care. It's not important. I'm going to start off with 2. That's where I'm going to start. Right? Now, we need a derivative. So my derivative is f prime of x is 3x squared, yes? Nice. So our formula is going to look like this. Negative 3x squared over parentheses x cubed minus 7 plus this xn bit. Okay. And that's going to spit out some x of n plus 1. And whatever I get for an answer, Angel, I'm going to run it back through again. Oh, and wherever these x sub n, these are all x sub n's as well. I'm going to run it right back through the formula again. I'm going to get a new x of n plus 1 out. I'm going to run it back through again. How will I know when to stop? Well, you'll watch. You'll see. It's going to be exciting. It's going to be really freaking cool, man. So let's go to, I'm going to pull up my Excel. You can use Google Sheets. They're all the same. It doesn't matter for this part of it. So over here, I'm going to make these my x's so I can keep track of them. I don't really care about the y's. It's not important. It's not important. So my initial x n was 2, but whatevs. And then here are my, you can call it my new values of xn. You can call it whatever. So I guess I'll do xn plus 1 or something. Whatevs. Okay. You could actually keep track of the y's too, I suppose, if you wanted to. It's not that important. So as our original function was equals x cubed, what, minus 7? What? So, okay, if you want to. And then Lil right here, what I'm going to do is this. You can do this a variety of ways. I mean, I'm not sure I want to do it this way, actually. You can do it a variety of ways. You know what? I changed my mind. Lose this column. I've done this about 1,000 different ways. Every time I do it, I find a different way I want to do it differently, okay? Whatever. Let's do y prime over here, shall we? Y prime. Whatever, okay? So what is the derivative? It's equals 3 times, is that right? 3 times x squared? Yes? That's it? Yes? No? Maybe so? Okay? Check it out. This is exciting. So if I wanted to find the new x, what would I do? Well, the recipe says you take negative the derivative divided by the function. Is that right? Or did I do that backwards? Look at the formula. Negative derivative. Oops, negative the function over the derivative. I got it backwards, didn't I? Darn me. Let's try it again, Mr. Groom, you idiot. Negative the function divided by the derivative. Oops, the derivative, yes? Right? Plus what? Plus the previous value of x. Do you see this? That's it. Yes? No? Maybe? Look at the recipe. Do you see the recipe? It literally says negative the function. That's what I did. Divided by the derivative. That's what I did, right? Plus the original value of x. Yes? Hit enter. What do you get? Oh my gosh, it's 1 point something. Huh? Now wait for it. Grab these guys and copy them down. Okay? I don't know how easy to do that is on this phone spreadsheet, but we'll try it. Now, grab these guys here. Watch me drag it away and see what happens, friends. Oh my gosh. Look what didn't change very much. After a while, what's happening to these x values? Well, they're not changing. Where are they not changing? I would argue they're not changing out to a bunch of decimal places, yes? I mean, wow. A lot. That's 10 decimal places, yo. It's not changing. What's the matter?
I was just curious about 12. Shouldn't that be like 36 and you do 3 times 2?
Did I forget something? It's 3 times 2 squared. It's 12, right?
Well,
2 squared.
Just saying to like the power of 2. Do you want 2 to the power of 2 or do you want 6 to the power of 2?
Well, 3x squared is 2 squared times 3. Please excuse my dear Aunt Sally, right? Okay? So there it is. So then you're like, wait a minute. How do I know how good I am, Mr. Groom? Check it out. So I could take 7 to the, we know how to do this, 1/3 power, right? That'd be the cube root of 7, right? And you're like, well, what was the whole point of that? The whole point of this is to understand an iterative process. So there are so many things in life and computer science and stuff that are iterative like this. It just keeps changing out. Look how far that is. Look how far out we are. 8, 3, 8, 3. But again, I didn't put any decimals to this guy. Let's add some more here. Oops. Let's add some more decimals. Give them to me, you hippie. There you go. Come on. There you go. Oh. And after like 10 or 12 decimal places, it says, screw it, it's close enough for government work. Okay. Now, what are we going to do? We are going to go, and as a general rule, I will tell you something. But here, I would tell you, hey, go until the first 5 decimal places match, or the first 7, or whatever it is. I can tell you go out as far as I wanted to go, and we could approximate this deal. Now, I'm going to go to Desmos.com. I'm going to make up a function because, well, I want to. Yeah. So x cubed plus x squared minus 1 x minus 1. Oh, no, not 1. Minus a half. There, that's pretty nice. Sure, looks like you've got 3 zeros there. Yeah, I know. That's good. Yeah. Where are they? No. But notice that one of them is just shy of 1. Yes? Notice that one of them is right around a half-ish. Negative a half-ish. And one of them is somewhere around negative 1.5-ish. Yes? Can you make note of that, please? So somewhere around 1-ish, negative a half-ish, negative 1.5-ish. Okay? So, what's that? What do you mean it didn't work on a phone? Yeah, so you're like, Mr. Grimm, it didn't work on my phone. Well, why you don't have a Bluetooth keyboard for your phone is beyond me. But no, I say today I take my 89 or my 83 or my Instinct, and I go into here and I go into y equals. Now, it's negative the function. What was our function last time? So I'm going to go negative parentheses. What was my function last time? Is x cubed, is that right?
Yeah,
minus 7. Divided by 3, oops, but make sure it's in a parentheses, you idiot. 3x squared, right? Plus x. Oops, and then I wrote 1. Plus x. That's important. It's important that you do that. Okay? Got it? You can do this in your TI 83, 84 as well, or your Inspire. or your TI emulator, whatever makes you happy. There's probably even a way to do it in Desmos. There's probably even a way to do it in Desmos so that it spits the answer out to a table. But I don't know how to do that. And I don't care, because there's about 8,000 other ways to make it happen. So just find a way that makes you happy. Now, go to the table, but table set first. So second table set up here. And you want it down here where it says independent, you want to say ask. It's a big deal. Okay? There you go. So go down there, it says auto, probably change it over to ask. Okay? And then go hit enter, make sure it saves, and then go, oh crap, notice how I didn't hit enter, now I've entered it, yes? That's important on the 89. I never hit enter, whoops. Now, go to diamond table, and then this pops out. You see it? You see it? Now, there should be nothing in there probably, because you just changed it to ask. So I'm going to type in 2. Boom. Okay. The Y is now my new X. So this is the cool thing about the 89. Come over here and go control, or the diamond, and then copy right here. And then come back over here, right there, get it there, give it to me. Oh, get an arrow over, sorry, I forgot. And then diamond paste, yes, hit enter, voila. And then come back over here, Control C, come down here, Control V, and ta-da, and what you're seeing is nothing's changing. Yes, it's the same basic process. I watched my Canadian guy this morning, so now I'm talking process. Does that make sense? Just Control C, Control V, it'll work the whole way down. It's great. Okay? Again, I do not care which of these technology pieces you use. Doesn't matter. If you want to use Excel during the test on the computer, you knock yourself out. I don't care. Okay? Do not care. Not even a little bit. Now, yeah, so let's do we need to do it? We need to do a new one. Here we go. Oh, what was my new one? It was x cubed. Was it plus x squared? Plus x? Minus x. Minus x minus half. Cool. And we said our values in question were about 1-ish, about negative a half-ish, and about negative 1.5-ish. Yes? So you do one at a time. We'll do one at a time. I'll start with 1, okay? But I need f prime first. So f prime is 3x squared plus 2x minus 1. So what's our recipe? It's negative the initial value, or the original function, divided by the derivative plus x. So if you're doing this in your calculator, you're going to type that thing into y equals. Notice that the only thing that's going to change between when you're doing it for 1, 0.5, and negative half, whatever, is where you start. It's the only thing that's going to change. Everything else is going to be the same process. You do not change this. You type this in one time, and then you're done. Okay? So I'm at 89. I guess I'll go 89 first this time. So click up here, clear this out. So negative parentheses was x cubed plus x squared minus x minus 0.5 divided by 3x squared plus 2x minus 1. Is that right? Plus x. All right? Lily, good? You good with this? You good with what we're doing here? Oh, yeah, cool. And then I just go to my table. And again, I just put in 1 first. Notice how it's 0.875, which is 7/8. So I can go over here and grab that, copy it, come down here and paste it in. Ooh, it's 0.855. Notice how we're good. We've now, the 8 hasn't changed, yes? So we're good to 1 decimal point, right? Keep an eye on it this time. Now come back, paste it in again. Notice how we're good to 2 decimal places this time, 0.85, yes? Let's do it again. Control C, Control V. What? we're good to 5 decimal places, huh? You see that? 0.85464 at least. We're good out that far, right? We could go further. That's enough, probably. Check it out over here on this graph. The computer just said screw it and ran it to 3 decimal places. We already kicked Desmos' butt in this deal. Okay. Now, let's look at Excel over here. This is disturbingly too many zero. Oh, Kim Kardashian. People don't get that reference. I'm like, hashtag Kim Kardashian. That's weird, Jay. All right, so our initial value was? What was our initial value? 1, right? Well, these are wrong. Well, duh, they're wrong. I have to change the function, right? So what was the actual function? It was equals this fella cubed, right? Plus this fella squared minus this fella minus a half. Oh, no. And then this one was what? Negative 3, no, 3x squared plus 2x. That's right. And then what? Minus 1. Bam. Now notice, first of all, this is freaking disturbing. I'm going to get rid of some decimals. It's starting to get on my nerves. There, that's more better. Well, let's go out a couple. That's bad. Bad form. There we go. Okay, cool. Now, why do they look so weird? Because I didn't paste these guys down, did I? I got to paste them down. Oh, look at that. 0.8546 seems to be our value. And of course, if a person wanted to, a person can always add a few more zeros. Oops. If the person clicked on the right column, it might actually work. A person can add a few more zeros. But clearly, we're good out to about 12 decimal places or something. This is pretty good. This is actually what the value is. Now, how do I change it if I want the negative a half one? I literally type in right here, negative half. Ta-da! Well, you said it was about a half, Mr. Groom. Well, it turns out I was wrong. It's 0.4030317, isn't it? And if you go to the graph, what? And then, by the way, on Excel, on your Doohoo, you put in negative 0.5. You have to cut and paste a couple of times. Yes. How many times? 1, 2. Well, 3 times and you're way done, for sure. Probably get by with 2, right? If I said 5 decimal places, you're golden already. But whatevs. And then the other one was about negative 1.5. So watch me plug in negative 1.5. What? So in reality, it's 1.4516060, blah, 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 blah. Yes? But Excel's it's a little bit nicer than 89, right? Back in my day, and I kid you not, do it by hand. Write all the numbers down, type it all back into your calculator. Because these numbers here, a guy had to figure out by himself. Jot them down, divide by this, make sure you don't drop a parenthesis somewhere. Because they weren't TI-83s with parentheses that you can see what you're doing. No. Where's that little calculator you always use all the time, Lacey? One of them little jobs, right? And you're like, it's weird. Now, these numbers should, come down and approach a value. Sometimes they didn't. That's because you screwed up. Now, this is section 4.8, which is page 213, right? Yes, page 213 you should be able to do tonight. Now, in this section, it's what we did today in class is just the Newton's method part of it, but we will do some other with the actual approximations later. Okay, so just the Newton's method part of it. Please, use your calculator. Use Excel. That's ridiculous. It's all about the technology. That's the whole point. All right?